In steady, gradually varied open channel flow, the longitudinal phase surface profile is called the backwater profile. It may be predicted using the differential form of the energy equation called the backwater equation, shown here, in which SF is the friction slope or slope of the total headline. Another expressions of the backwater equation are shown here as a function of the specific energy E on the water depth D. One may look at a relevant YouTube video movie on the same topic. This sketch shows the definition of the cross-section area, free surface width and weighted perimeter, all measured perpendicular to the streamlines ends of the flow directions. In gradually varied open channel flow, the longitudinal variation in water depth, that is the variation of water depth with respect to longitudinal distance x, is a function of the relative magnitude of the flow depth, the critical depth, and the uniform equilibrium depth. First, let us remember that the momentum principle applied to a steady uniform equilibrium flow gives us S0 equal SF, where S0 is the bed slope and SF is the friction slope. When the bed slope is less than the friction slope, the velocity is greater than the uniform equilibrium velocity, and the water depth is less than the normal depth, with the expression of the uniform equilibrium velocity V0 shown here. Conversely, when the friction slope is less than the bed slope, the water depth is greater than the normal depth. Second, let us remember the basic definition of sub and supercritical flow. A subcritical flow, that is, the water depth being greater than the critical depth, corresponds to a Froude number less than 1. Conversely, a supercritical flow, that is, a water depth less than the critical depth, is associated with a Froude number greater than unity. Altogether, there are 12 different types of free surface profile in steady, non-uniform gradual varied flow, excluding uniform equilibrium flow, with 2 physically meaningless profiles among these. In this table, the far right column indicates the name of the profile with the first character, describing the longitudinal bed slope, H for horizontal, M for mild, S for steep, A for adverse. One may look at a video on mild and steep slope. This sketch shows the possible free surface profiles for a horizontal slope, S0 equals 0. Note that only 2 profiles are physically possible, since the uniform equilibrium depth is infinite in a horizontal channel. This second sketch presents the 3 possible backwater profiles for a mild slope, D0 greater than DC. The profile M1 corresponds to a subcritical river flow reaching a reservoir, for example. The profile M2 could be a subcritical flow reaching an overfall or a change to a steeper slope. The profile M3 could be a supercritical flow situation, for example, downstream of a sluice gate. For a steep slope, D0 less than DC, there are 3 possible backwater profiles. The S1 profile may correspond to a subcritical flow downstream of a hydraulic jump, for example, when a steep stream reaches a reservoir controlled by a gate. The profile S2 could be a supercritical flow downstream of a weir crest or at a change from mild to steep slope. The profile S3 would be a supercritical flow situation, for example, downstream of a sluice gate discharging into a steep slope. The last sketch shows the backwater profile for an adverse slope. Only 2 physically meaningful profiles may be observed. The profile A2 may correspond to a subcritical flow approaching an overfall at the downstream end of an adverse slope. The profile A3 corresponds to a supercritical flow on an adverse slope, for example, on a spillway approaching a ski jump. Strictly speaking, there are 3 more backwater profiles for critical slope, D0 equal DC, most rarely encountered in nature, as well as a couple of profiles for a vertical slope. Importantly, the typology of free surface profiles is valid for prismatic channels only. Any change in flow rate, invert slope, boundary roughness, or cross-sectional shape may induce a change in critical and normal depth, hence in backwater profile type. The concepts of backwater profiles and backwater calculations are essential to the hydraulic engineering of open channel flow and its practical applications, including flood modeling, that are discussed in a number of relevant YouTube video movies in the same playlist.